One of the successful models that create an intellectual framework within which to clarify network concepts and activities is the Open System Interconnection, or the OSI reference model, proposed by the International Organization for Standardization, or ISO. This model is sometimes referred to as the ISO or OSI reference model. The OSI reference model has become a key part of networking because it is so widely used and supplies so much important network terminology. To illustrate the value of the layer concept, consider the process of purchasing mobile phone service. All the functionality of each option and feature involved in the mobile phone service can be broken into layers. Just like cellular phone service, computer networking, computer compatibility, and networking features and functions can be a challenging subject to grasp. However, it would be so much difficult to comprehend if not for the fact that networking is built on a common framework and the process is broken into layers. This is the idea of the OSI model and its 7-layer approach to networking. The real value of the OSI reference model is that it provides a useful way to describe and to think about networking. One word, layers, conveys the essence of the OSI reference model. This model's foundation rests on the idea that networking can be broken into a series of related tasks, each of which can be conceptualized as a single aspect, or rather a layer, of the communication process. Computer scientists like to call this divide and conquer because it creates a method to solve big problems by deconstructing them into a series of smaller problems with individual solutions. Understanding layers. So a number of tasks has to be completed to deliver a message. All were separate tasks, but for one task to be completed, the previous task or layer had to be completed correctly. For example, the letter had to be addressed in a correct format. The local post office in New York had to sort the letter correctly and get in the right plane to San Francisco. The post office in San Francisco had to sort the letter correctly for the correct part of town. And lastly, the local area had to deliver the letter to the correct house. The OSI reference model for networking makes explicit many communication activities and related tasks and requirements. This frame of reference clarifies what networks are and how they work. The structure of the OSI reference model breaks down all the events that must occur for the data to be properly addressed and formatted before it can actually be delivered to its final recipient. To fully comprehend the model's function, it's necessary to understand how it behaves as a whole. At the outset, any computer that can access a network must be endowed with a protocol stack, also known as protocol suite. Protocol stacks provide the software that enables computer to communicate across a network. Currently, the most common protocol stacks include Transmission Control Protocol, Internet Protocol or TCP/IP, the Inter-Network Packet Exchange and Sequence Packet Exchange or IPX/SPX, NetBIOS, Enhanced User Interface or NetBEUI, AppleTalk, and Systems Network Architecture or SNA. These protocol stacks, combined with drivers for whatever network devices are attached to a computer, provide a crucial software link that permits applications to communicate with the network. Taken as a whole, protocols plus drivers equals network access. So each individual layer in the OSI model has its own set of well-defined functions, and the function of each layer communicate and interact with the layers immediately above and below it. Rigidly specified boundaries called interfaces separates layer in the OSI reference model. Any request from one layer to another must pass through the interface. In the reference model, layer construction follows an abstract concept called peer layers. That is, each layer on one computer behave as if it were communicating with its twin on the other computer. This is sometimes called logical or virtual communication between peer layers. On its way down the stack, before data gets passed from one layer to the next, it is broken down into data units, sometimes called as packets or payloads. This official acronym is PDU, sometimes interpreted as Protocol Data Unit, Packet Data Unit, or even Payload Data Unit. The PDU is a unit of information passed as a self-contained data structure from one layer to another in its way up or down the stack. The special formatting or addressing added to the PDU is referred to as a header, and the process of adding this header is called encapsulation. The stripping of the header from the PDU is referred to as de-encapsulation. Application layer or layer 7. This is the top layer of the reference model. It provides a set of interfaces for applications to obtain access to network services as well as access to the network services that supports application directly, including services such as network file transfer, message handling, and database query processing. This also handles general network access, the movement of the data from sender to receiver, and error recovery for application where applicable. The PDU in this layer is referred to as simply as data. Presentation layer or layer 6. This handles data format information for network communication. This layer also handles protocol conversion, data encryption or decryption, character set issues, and graphic commands. A special software facility known as redirector operates at this layer. Session layer, layer 5. The session layer permits two parties to hold ongoing communication, called a session, across a network. This means application on either end of the session can exchange data for as long as the session lasts. This layer handles session setup, data or message exchanges, and tear down when the session ends. It also monitors session identification so only designated parties can participate, and monitors security services to control access to session information. The session layer also manages the mechanics inherent in any ongoing conversation, including identifying which side may transmit the data, when and for how long, and maintaining a connection through transmission of so-called keep-alive messages, designed to keep inactivity from shutting down an open connection. Transport layer or layer 4. So layer 4 manages the conveyance of data from sender to receiver across a network. It segments arbitrarily long data payloads into chunks that match the maximum packet size for the networking medium in use. Includes error checks to ensure error-free delivery, and handles resequencing of chunks into the original data on the recipient. The transport layer also handles flow control. The PDU at this layer is called a segment. Network layer or layer 3. Network layer handles addressing messages for delivery but also translates logical network addresses into their physical counterparts, which are known as a MAC address. This layer also decides how to route transmission from sender to receiver. This layer is also the traffic cop for network activity and handles packet switching, data routing, and congestion control. The network layer also handles fragmentation and reassembly functions based on the disparities between dissimilar media. Data link layer. So layer 2 sends PDUs from the network layer to the physical layer. The PDU at the data link is called a data frame or frame. A data frame is a basic unit for network traffic on the wire as sent across the medium. In more general terms, it's a highly structured format within which payload data from upper layers is placed for sending and which payload data from upper layers is taken on receipt. The destination ID provides a network address for the frame's intended recipients. The sender ID provides the return address for the frame sender. Control information covers a multitude of topics from identifying specific frame types to providing routing and segmentation data. The data integrity check, called cyclical redundancy check or CRC, is a special mathematical function based on the bit patterns in the frame. Sent as part of the frame itself, the CRC is recalculated on the receiving end. The data link layer handles delivery of frames from sender to receiver through the physical layer and across the network medium. The data link layer is responsible for detecting errors in the transmission of frames and discarding those frames that arrive containing errors. The software component that operates at this layer is the NIC driver. Physical layer or layer 1. Its job is to convert bits into signal for outgoing messages and signals into bits for incoming one, meaning the physical layer orchestrates the transmission of whatever form a data frame's bits take when dispatched across the network medium. The physical layer manages the computer's interface to the network medium and instructs the driver software and the network interface what to send across the medium. The physical layer is where specification of all the details for creating a network connection occurs. These include how the medium attaches to the NIC. The physical layer also handles the intricacies of transmitting the pattern of bits that represents a date frame from the sending to the receiving computer, even those bits are arbitrary at this layer. Encoding is a representation of zeros and ones as a physical signal, such as electric voltage or light pulses. Although the OSI model is not strictly adhered to by all networking protocols, a network's administrator's clears the understanding of the function at each layer is paramount to the troubleshooting process and to understanding how networking devices operate. The Institute of Electrical and Electronic Engineers, or IEEE, launched an effort to define a set of LAN standards to ensure that network interfaces and cabling from multiple manufacturers would be compatible as long as they adhered to the same IEEE specification. This effort was called Project 802 to indicate the year and the month of its inception. Project 802 concentrates its efforts on standards that describe the physical elements of a network, including network adapters, cables, connectors, signaling technologies, media access controls, and the like. The 802 specification documents describe how NICs may access and transfer data across a variety of networking media. They also describe what's involved in attaching, managing, and detaching such devices in a network environment. IEEE codified the various efforts undertaken as a part of Project 802 in a number of standard categories number 802.1 through 802.20. The IEEE 802 specification expanded the OSI reference model at the physical and data link layers, which define how more than one computer can access the network without causing interference with other computers on the network. The 802 standards provide more detail at these layers by breaking the data link layer into the following sublayers. So the first one is the logical link control, the LLC, for error recovery and flow control. And the second one is the Media Access Control, the MAC, for access control. The Logical Link Control, or LLC, sublayer controls data link communication and defines the use of logical interface points, called Service Access Points, or SAPs, that other computers can use to transfer information from the LLC sublayer to the upper OSI layers. The LLC is also responsible for error recovery in some situations. So the Media Access Control, or MAC, sublayer provides shared access for multiple NICs with the physical layer. The data link address burned into every NIC's PROM is called a MAC layer address because it operates at this sublayer of the 802.2 specification.